Hello everyone and welcome back to StatsTree. In this video, we're going to be talking about basic probability. I wanted to start with this quote about probability. Anything at all is possible. Some things are unlikely. Some things will never happen, but they always could at any time. I like this quote because I think it gets across the magical properties of probability that are this really interesting mix of fundamentally important and profound, as well as being pretty vague. And what I hope to do in this video is to wade through some of that vagueness to help to give you a better understanding of the basic principles of probability and why it's important. So we care about probability because it's central to biology and statistics. And the reason for this is our need to collect statistical samples. And anytime we collect a statistical sample, chance can play an important role. As a result, we need to get comfortable with the idea of chance and probability if we want to understand about statistics. So we all know that the probability of selecting a red card from a deck of cards is 50%, and there's a 50% chance of selecting a black card. But how do we know this? Well, selecting a card from a deck of cards is a representation of what's referred to as a random trial. A random trial is simply a process with two or more possible outcomes that we can't predict in advance with certainty. And in a random trial, only one outcome is observed per repetition. So think, for example, of dealing only a single card at a time. The dealing of each card represents a unique random trial. So what is probability then? Probability simply represents the proportion of times that an event would occur if we were to repeat the random trial many, many times under the same conditions. Probabilities are restricted to range between 0 and 1, where a probability of 0 represents an event that can never happen, and a probability of 1 representing an event that will always happen, and probabilities between 0 and 1 representing something in between. The higher the probability, the more likely an event is going to happen. We can calculate a probability then as the proportion of all possible outcomes in which the event could occur. So our probability of drawing a red card then is represented by 26 possible outcomes. There are 26 red cards in a deck of cards out of a total of 52 cards. So our probability of drawing a red card then is 26 out of 52, which is equal to 0.5. There's a 50-50 chance of drawing a red card from a deck of cards. Similarly, we can calculate the probability of rolling a 6 on a 6-sided die as 1 out of 6. Now, rolling dice and dealing cards isn't very biological, but these basic principles are familiar to most of you, and these random trials that we get from rolling dice and drawing cards is really similar to the process that we engage in when we collect a random statistical sample from a population. So let's go over a few principles of probabilities. First of all, the probability of all possible outcomes must always sum to 1. So we can calculate the probability of rolling a 1 on a 6-sided die as 1 out of 6. Similarly, we can calculate the same probability for a 2, for rolling a 3, a 4, a 5, and a 6. And all of these probabilities of 1/6 need to sum to 1 because we need to account for all possible outcomes from our random trial. This might remind some of you of your genetics class when you learned about Hardy-Weinberg equilibrium and the truism that P plus Q must always equal 1. P is the frequency of, say, the big A allele, and Q is the frequency of the little a allele. And the frequency of the big A allele simply represents the probability of drawing a big A from a pool of gametes. So in Hardy-Weinberg equilibrium, we often remind everyone that P plus Q must equal to 1. And this is simply representing the fact that all possible probabilities, or the probabilities of all possible outcomes, must sum to 1. In order to talk about other properties of probabilities, we need to define what are called mutually exclusive events. Now, two events are defined to be mutually exclusive when they cannot occur at the same time. This is what we mean by mutually exclusive. So then the probability of having A and B happen is equal to 0. So when the probability of A and B happening is 0, we define those two events, the event of A occurring and B occurring, as being mutually exclusive. So for example, when we roll a die, it must come to rest with one number showing on the top. So you can therefore roll a 4, or you can roll a 6, but you can't roll a 4 and a 6 at the same time. So the probability then of rolling a 4 and a 6 with a single die is equal to 0. So that event of our random trial of rolling a die, the event of a 4 turning up and a 6 turning up on a single die, are mutually exclusive. The next principle we want to talk about is the probability of not. And what I mean by that is the probability of an event not occurring. Now, if you remember that the probability of all of our occurrences needs to sum to 1, then we can define the probability of an event not happening as being equal to 1 minus the probability of the event happening. So if the probability of rolling a 4 on a 6-sided die is 1 out of 6, then the probability of not rolling a 4 needs to be equal to 1 minus the probability of rolling a 4, which is equal to 5 out of 6. Now that we've covered these properties of probabilities, we can talk about some rules for how we deal with multiple events. The first is that we can add probabilities together to represent the occurrence of either this event happening or that event happening. So we can define our addition rule as being that the probability of A or B happening is equal to the probability of A happening plus the probability of B happening, as long as these two events, A and B, are mutually exclusive. So if we look at these probabilities of different blood types in a population, and we know that blood types are mutually exclusive, you cannot be O negative and A positive at the same time, then we can calculate what the probability of having an O blood type is by summing together the probability of being O negative and the probability of being O positive. So we can sum together these two probabilities to calculate that the probability of being O negative or O positive is equal to 0.44. So what about a situation when two events aren't mutually exclusive? That is, when two events can happen at the same time. Well, here I've drawn a little schematic diagram of some shapes that could be circles or squares, and they could also be orange or purple. But you can see from the way I've drawn this that the shapes can be both purple and squares at the same time. So the shape and the color are not mutually exclusive. So what if we wanted to add together probabilities then of two different events happening? So the probability of A or B happening when we have events that are not mutually exclusive is a little bit more complicated than the example we had before. To calculate the probability of A or B happening, we need to add together the probability of A, the probability of B, and subtract the probability of both A and B happening at the same time. So let's work through this example. We might be interested in the probability of the shape being either purple or square. To calculate this, we would add up the probability of it being purple plus the probability of it being square minus the probability of it being purple and square at the same time. So from our example, 3 out of 8 outcomes were purple, 4 out of 8 outcomes were square, but 2 out of 8 outcomes were both purple and square. So we add 3 8s and 4 8s, but subtract 2 8s to come up with our probability that the shape is either purple or square as 5 8s. And this last part, the subtraction of the probability of this and that happening, avoids the double counting that we would get as a result of the events not being mutually exclusive. Now, in addition to events being mutually exclusive or not mutually exclusive, two events can also be either independent or dependent on one another. We can define two events to be independent if the occurrence of one event does not affect the probability that the second event will occur. So for example, whether or not I ate cereal for breakfast is independent of whether or not it will rain today. Knowing that I ate breakfast cereal this morning doesn't change what our underlying expectation is that it will rain today. If two events are independent of one another, then the probability that they both occur together is equal to the multiplication of the two probabilities. So the probability of A and B happening is equal to the probability of A happening multiplied by the probability of B happening. So in my silly example that I gave you above, the probability that I ate cereal for breakfast and it rains is equal to, let's say, 0.4 times 0.05 to come up with a probability of me eating cereal in the morning and it later raining that day of 0.02. Now, I've just made up numbers to go with this, but I hope that you get the basic idea. So let's recap the difference then between the probability of this and that happening as opposed to the probability of this or that happening. When we're interested in the probability of two events happening at the same time, the probability of A and B, we calculate this by multiplying the two probabilities together. In contrast, when we're interested in the probability of either this or that happening, we sum the two probabilities together. And as long as the two events are mutually exclusive, we can simply sum the probability of A and the probability of B. If A and B are not mutually exclusive, then we need to remember to subtract the probability of A and B happening to avoid double counting. When tracking probabilities across multiple events, it can be helpful to use what are called probability trees. And probability trees are just diagrams that depict possible outcomes and their associated probabilities. So if we are to consider the probability of a human giving birth to a boy or a girl, we can see that the probability of giving birth to a boy is actually slightly higher than the probability of giving birth to a girl. And so the two arrows to boy and girl represent the two possible outcomes, and the numbers along the arrows represent their probabilities. Now, of course, this is a very simple scenario where we wouldn't really need to make use of a probability tree, but we can get a little bit more complicated. Here we have a little bit more complicated probability tree that depicts the possible outcomes from two successive events. For example, the birth of two children. Here we have the first event, which is the sex of the firstborn offspring, and the second event on the right is the sex of the second-born offspring. And we can see that there are four possible outcomes corresponding to firstborn boy, firstborn girl, second-born girl, and all the different combinations. And you can see that the probability of giving birth to a boy at any one birthing event always stays the same. But we can use these probabilities trees then to calculate what the probability is, for example, of giving birth to two boys. Okay, and to calculate that then, we need to know what's the probability that the firstborn is a boy and the secondborn is a boy. So in this case, we're then multiplying those two probabilities together. And that's what's depicted by the probability tree. We have one arrow of 0.512, a second arrow of 0.512. So the probability of giving birth to two sons is 0.512 times 0.512, which is equal to 0.262. So if you have two children, there's a 26% chance that both of them will be boys. You can perform similar calculations to find out that there's a 24% chance that both offspring will be girls, and a 50% chance that one boy will be born and one girl will be born in a family of two. My wife and I have 3 daughters, and we could extend this probability tree further to calculate the probability of us having all 3 offspring be girls is 0.116. Now, before we talked about independent events, where the outcome of one event didn't give us any more information about the probability that a second event would occur. But multiple events are obviously not always independent. Sometimes the outcome of one event influences the outcome of a subsequent event. In this case, the variables are considered to be dependent. So we've already talked about some equations that we can use for calculating probabilities based on independent events. And so what we can do is to look at situations where those probabilities, assuming independence, don't match what we actually see. And from that, we can infer that the events actually aren't independent, that the outcome of one event is actually influencing the outcome of the other. So for this part of the video, we're going to talk about a really interesting example, which is the jewel wasp. Now, the jewel wasp is a parasite. It lays its eggs on the pupae of flies, which we always call maggots. And the larval wasps hatch inside these maggots and feed on the living maggots themselves, eventually emerging and developing further themselves. Now, adult jewel wasps have a really remarkable ability to manipulate the sex of the eggs that they lay in their maggot hosts. When a female finds a fresh host that hasn't already been parasitized, she lays almost exclusively female eggs. But interestingly enough, if the host has already been parasitized by a different wasp, then the female responds by producing almost exclusively sons. So for this example, let's assume that 20% of maggots are already parasitized by jewel wasps. So what we can do then is to combine this information about these two events. What is the probability that the host is already parasitized? What is the probability that an individually laid egg is a male? So we can use our probability tree to calculate what some of these complex probabilities are across multiple events. So to begin with, remember that we said that there's a 20% chance that the maggot is already parasitized. So there's a 20% chance that the host is already parasitized. Because of our rule of naught, that means there's an 80% chance that it's not parasitized. These two probabilities represent the only possible outcomes. They need to sum to 1. Now, if the maggot is already parasitized, then the probability of a new egg being male is 90%, and the probability that that egg is female is 10%. In contrast, if the maggot is not parasitized, then there's a 95% chance that a new egg laid will be female and a 5% chance that it's male. So what if we were interested then in calculating what the probability was of a new egg being male? What we would need to do then is to sum together the probability of this outcome, a male being laid on a parasitized maggot, together with this outcome here, which is a male egg being laid on an unparasitized maggot. So we can take these two probabilities and add them together and say that overall, under this scenario, the probability that any egg being laid, regardless of whether the host is parasitized or not is 0.22. Now, we previously stated or assumed that the probability that the host was parasitized was 0.2. And we can use our basic probability principles to say that if these events are independent, meaning if the parasitism of the maggots is independent of the sex of the egg laid, then we expect that the probability that the egg is male and that the maggot is previously parasitized is equal to the probability that the egg is male multiplied by the probability that the maggot is previously parasitized. So we expect if these events are independent for the probability of the egg being male and the maggot being previously parasitized to together be 0.044. And what we can do then is to see how this compares to what we actually observed from the probability tree to see whether or not our assumption of independence of these events is actually correct. And what we find when we look at the probability tree is that the probability egg being male and the maggot being previously parasitized is actually much higher. It's 0.18. And so we can conclude, in fact, that these events are not independent, that the probability of laying an egg that's male is influenced by whether or not the maggot had been previously parasitized. And we can depict this using a particular kind of Venn diagram called a mosaic plot, where each of the 4 possible outcomes are represented by the sizes of these boxes. And the boxes are color-coded to represent male and female, males in blue, females in brown. And what we can see is that the sizes of these blue boxes in the different parasitism scenarios are not at all the same. We can see that when hosts are not parasitized, most eggs are female, and when the host is parasitized, most eggs are male. So the probability of laying a male egg is not independent of the previous event, which is whether or not the maggot was already parasitized. So to summarize what we've learned about basic probability then, we've learned that probability is an important concept in biology because random sampling represents a random trial. So we need to get comfortable with probabilities if we're going to understand sampling and statistics. A probability simply represents the proportion of times the event would occur if we repeated the random trial many, many times. The probability of all possible outcomes always sum to 1. 2 events are mutually exclusive if they cannot both occur. And 2 events are defined to be independent if knowing the outcome of one event provides no further information on the outcome of a subsequent event. If we know about whether events are independent or mutually exclusive, we can use our addition and multiplication rules to calculate the probability of either of 2 events happening or of both events happening together. So I hope this video has provided you with a better understanding of the basics of probability and that we'll be able to use this information and new knowledge in some of our subsequent videos.